The NEC recommendation. Although the NEC generally does not include rules for voltage drop, it does contain several recommendations. 210.19A1, Note 4, we talked about that. 215.2A, and I guess if I had to do this again, I'm going to change this, Steve, to 215.2A, and that would be simply Note 2, right?
Yeah.
Because it's not a note to number 4, it was just a note to 215.2A, Note 2. We need to make sure that textbook has that in there. All right, so here's 210.19A1, Note 4. 3% is the maximum on the feeder. And it says the maximum of the maximum of the branch circuit is going to be 3%. And the combination is not going to exceed 5%. Steve?
I think on that last one, Mike, we actually were rounding the wrong way. If we round 0.6, we actually were a couple tenths of a volt too low on that.
Say that again to me here.
We came up with 197.6, and we actually were supposed to have 190. We're supposed to have 197.6 or more. So if we actually have 197, we're 6 tenths of a volt low.
Oh, you're saying that if the minimum at 5% was
197.6 was our
197.6.
So yeah, we rounded to 198 in that top.
Well, even if we did round it off, if the minimum was supposed to be 197
yeah, we're 6 tenths
or 97.6, this is actually below the 5%.
Yeah, we're just a little bit low on that.
Let's take a look at this graphic here. And in this graphic here, this 210.19A1 Note 4 only applies that the branch circuit is 3% and the feeder combination is 5%. The reference about the feeder being able to be 3%, this rule is going to be 215.2A Note 4.
Note 2.
Yeah. Note 2. 215.2A Note 2 says that the feeder can be up to 3%, but then the combination cannot. So this heading right here would have two rules, right? 210.19A1 Note 4 and 215.2 Note 2. A2, whatever. You got it. Okay. So now, here's the heading right here. This one will be correct. Okay, so let's take a look at this. All right. Real simple. I got a 120-volt circuit. What's the minimum voltage at the load if you have a 120-volt circuit? Well, the maximum of the feeder and the branch circuit, no matter what we do, however we figure it all out, it comes out to be 5%. 5% less 120. It should not be less than it's recommended not to be less than 114. What's the maximum of the feeder? 3%. Maximum of the branch circuit, 3%. Maximum of the feeder and branch circuit, 5%.
And that's if you're at 120 at the source, correct? I mean, because you could vary. Correct me if I'm wrong, Mike. I mean, if I took a meter to a service any place and I get 121, I go across the street, I read 119.
Well, what we're talking about works really well for exam preparation, but not in reality.
Right. Okay.
Because when you get in reality, it's a little different ball game. And in reality, it's like we don't have 120 volts. It could be 116 volts.
Today.
It could be 128 volts. And this morning it's a higher volt, or last night it was a low, higher. In other words, it's always a moving target. In the real world, what you're trying to do is you're trying to limit the voltage drop to 5%, okay? But in the real world, you need to know is, well, what's your voltage that you have? And the easiest way to do that is figure, okay, yeah, but what is the voltage that the equipment needs to be rated at? If the equipment has a voltage rating plus and minus 10%, then as long as we fit within the plus and minus 10%, we're okay with the equipment. You follow my logic? So now what I have to know is that if I have a 208 volt, 120 volt piece of equipment, I could lose 10%. That's the standard voltage rating. I could lose how many volts? 12 volts.
12 volts.
So that's 10%. However, my voltage source, who knows what that voltage is going to be? So you're going to have to try to find out, okay, what's the normal voltage that's going to be there? And it gets to be such it's really tough. Well, Mike, I'm starting at 116 volts. Do I go 5% 116? Hey, Mike, I'm in a location, I got 126 volts. Do I use 126 volts at the 5%? But why would you use 126 volts and 5% limit to 5% when you already had it started at 8 volts higher than the other neighborhood, because the other neighborhood utility gave you a lower voltage because you're at the end of a power line, so the voltage is lower. You see the dilemma that's there?
yeah.
These are really power quality issues. That's why the NEC says what? This is really, for exam preparations, is easy. I have a 120 volt source. What's the minimum voltage at the load? Okay, well, you have the source. You got a 5% volts drop. 5% of 120 is going to be 6 volts, right?
Yes.
6 volts minus 120 is 114. Easy. But when you get in the real world, it's informational. It's like, well, what do you want it to be? What do you care about? What's important to you? I don't really care. I'm all incandescent lighting. Well, if it's incandescent lighting, it's irrelevant. Oh, I'm operating motors. So it becomes a power quality. Really, the information note is really talking about power quality. How important is it to you that you have the voltage at the equipment to perform its function? And once you know that, I say, okay, I measure my voltage during a time that this. Example, night lighting. If you got night lighting in there, is it possible that when the lights come on at nighttime until the time they come back off again, that voltage will be higher on that system than it would be during the daytime? Yes or no?
Very much so.
What do you guys think?
Definitely.
Yeah, because the utility load is down. Therefore, what happens to the voltage? It goes up. So if you were really trying to work on power quality, I'd find, okay, well, at nighttime, I go there, measure nighttime. What's my voltage? Oh, it's 126 volts at nighttime. But if you measure yourself at 8 o'clock, 10 o'clock in the morning, it's 115 volts. Well, I don't really care what the voltage is in the morning. It's 115 volts at night. It's 126 volts at nighttime. But what about if you're operating and you're going to be putting a piece of equipment in that's motors? And it needs operated at a certain given voltage, because, Eric, you talked about that if you don't get the right voltage to a motor, the motor starts running hotter.
Right.
As the heat goes up, then the life of the motor,
goes way down.
it goes down.
Yeah,
Way down.
It just goes way down, precipitously down. And so, therefore, what we're trying to do is, if it's power quality, we know we're already starting at a lower voltage at the time of the day that this motor is going to be operating. Power quality, informational note, right? That's why it's not a code rule. Then you need to consider this for reasonable efficiency of operation, that you might now have to realize that, okay, the motor needs to get this voltage. I have this here. I wouldn't be worrying about the 3 and 5%. I'd be working on the numbers that's practical. Then you do the calculation, you realize I need 500 thousandths of that motor. Like, I guess I really don't care if it's that efficient. Maybe I then need to bring the wire size down so I can sell the job to the customer. So this is where, see, when you're working code and you're working an exam, that's a science, okay? But when you're a professional and you're in the field, that's when it becomes art. That's when you have to start making judgment calls. You have to start using intuition. You have to start using experience. You have to start becoming creative to take care of the customer need. So it's kind of tough to ask that question to me in this setting, because I have to have, which hat am I? I'm teaching a class. It's real simple. Don't worry about it. It's 120 volts. You take your 5%, it's 6, 114. Take the hat off. You say, okay, Mike, I'm in the field. Well, a different story. Now we're talking about art. Now we can get a little creative because it's power quality. I don't know if I got too much or not, if that helped it.
I was just sitting here, if I'm looking at this going, man, this doesn't seem right, because this is what I dealt with yesterday, and now what do? I have 126, like you said, volts. Now what do? Do I use a higher percentage?
But did I answer your question?
Yes. Oh, yeah.
Code-wise, it's science. This times this. You get in the field, you got to learn, what does this load need? Where am I starting at? What's the time of the year that it's taking place? And then I work those information together for us to be able to make the best decision. And when we get to the end of this program here, we'll work a couple examples like that, and we'll see how it works out. Stephen?
And in the field, it makes so much difference what you're actually servicing. Are you servicing a computer or electronic equipment, or is this just an underground feeder going to a livestock water that you're going to keep the ice off in the winter? Because if you had livestock water, whether the voltage is 200 volts or 240, it's going to still do its job.
It's a heater, and that's a brilliant point. Resistive loads, when you have a resistive load and you drop the voltage of resistive load, all what happens is that load doesn't heat up to the level it was designed for. You have a resistive load that's rated 1 kW at 120 volts. Well, if you start dropping down the voltage, okay, see, P is equal to E squared over R. That resistance pretty much doesn't change in that resistive load. But if the power is E squared over R, if it was 120 squared over the resistance, then you get, let's say, 1,000 watts. But as you start dropping down the voltage and you square the voltage and you go down 10% of the voltage, well, 10% of the voltage is 90% of the voltage squared, and that comes out to be what? 81% of the power. So power, when it comes to resistive load, is by the square of the voltage. But if I have a piece of equipment out there and I got a heater out there and it's a long distance and it's 10% voltage drop, well, it's not what? It's not a 1 kW load. It's going to be an 800 watt load, and the heater's going to be cycling a little longer on and off than it might have been if it would have been a 1 kW load. It doesn't matter. It's a resistive load. You got a long incandescent light bulb. The light bulb is going to last a long time.
That's right.
Because we've reduced the voltage, which we reduced the luminous output, we reduced the power of the light bulb, we reduced the heating of the light bulb incandescent. Now you might have electronic ballast, so compact fluorescent fixtures. I don't know what loads are more sensitive to voltage. And this is a great conversation, is that when we're in the field, we need to take care of our customer. We need to understand what are the loads, what are the needs, consider the power quality ramifications. What are the loads going to operate at the time they're going to operate? What's the voltage utility of the system? We might even have to go to utility and say, hey, listen, we got a problem here that we're not having enough voltage bringing to this building. So utilities have voltage ranges. They have to supply voltage to you. They have to. There's an ANSI standard, and I think it's plus 6% and minus 10%. They can't give you more than 6% of the rating, 120 plus 6%, but they can go down below. I think it might be not 10% below. It might be less than that. It might be 6% less also, 5% less. There's a standard in there. But it's possible over time they added more people on the system, and all of a sudden that voltage goes down. Nobody calls them. But you get there and you realize this voltage is starting too low before I get to that load. Then you get the utility, change the transformer, change the system. So I know that's, you're like, what's that have to do with exam prep? But nothing. But we're here to make you a leader here. We're not here just to teach you only the science. We're here to teach you the art part of being able to solve problems and understand a real problem. You said, understand, nothing to do with the exam, having to do with being finessed to be able to solve the problems. Did it help a little bit?
Yes. Thank you.
Okay. All right, back over here. We're going into the science of exam preparation. 120 volts at 3% is 6 volts. It gives me 114. Bada boom, bada bum. I'm done. Next one. Under voltage for inductive loads can cause overheating, inefficiency in a shorter lifespan for the electrical equipment. We talked about that. Is that right? Does the code care?
No.
No. It says, hey, want to tell you about it. You know, a little note there in 210.19a1 and then 215.2a. You know, think about this. Yeah, I don't care.